Hi everyone, my name is Ramesh. I am working as an associate professor in the Department of ECE, MLR Institute of Technology. Today we are going to learn about analysis of CC amplifier using hybrid model, common collector amplifier using hybrid model. In the previous lecture, we discussed about common emitter amplifier with using hybrid pi model. So in common collector configuration, what we will discuss is in today's session, we discuss about what is a CC amplifier circuit, AC analysis, what is the AC equivalent circuit for the common collector amplifier, H parameter model for AC equivalent circuit, current gain, input impedance, voltage gain and output impedance, and we will discuss about the characteristics of common collector amplifier. So let me go into the common collector amplifier configuration. Let us consider NPN transistor connected in common collector configuration. The input is applied to the base terminal. Let us take the bypass capacitance, the coupling capacitance is CB here, and we will consider the source, DC source as VCC, and we will take a resistor here, RL, which is acting as a load resistor, which is connected between emitter and ground terminal, and we will take a coupling capacitor at the output. Let us take this coupling capacitor as C0, and we will take the output across the emitter terminal. Input is given to the base terminal and output is taken across the collector emitter terminal. Now for collector we are applying a VCC. Now this is the actual common collector amplifier circuit. The input AC signal is applied to the base terminal and we are taking the output across the emitter terminal. Now for AC analysis, what are the conditions we need to consider? For AC analysis, we will consider the effect of DC sources becomes zero, that is nullifying the effect of DC sources, and whatever the capacitors which are present in the circuit, we will consider them as a short circuit because the reactance of the capacitor is 1 by 2 pi Fc. As frequency increases, what happens to the reactance of the capacitor? Reactance of the capacitor decreases, so that logically they are considered as a short circuit, and we will nullify the effect of DC source. The DC source must be grounded. So let us discuss the conditions here. For AC analysis, what we have to do, we have to draw the actual circuit diagram of the common collector amplifier that we just now did, and now replace the coupling capacitors and bypass capacitors by short circuit, because as frequency increases, reactance decreases. For AC analysis, nullify the effect of DC sources and replace transistor with H parameter model. So if you see here, what is the AC equivalent circuit? Whatever we are having here, VCC must be grounded, nullify the effect of DC sources, and we need to consider this as short circuit. The capacitors will be short circuited, and what will be the equivalent circuit? AC equivalent circuit is, consider the same circuit here, and we are taking this as short circuit, and across which we are taking the output, and this will be grounded here. The coupling capacitor CB is also short circuited, and we have a RS source, the source resistance along with the source voltage Vs, and VCC is grounded. This is called as AC equivalent circuit. Now the collector is directly grounded here, and we are taking the output across the RL. So let us go for the H parameter model for this particular AC equivalent circuit by considering the transistor H parameter equivalent model by connecting external elements like RS and Vs and RL. So next, H parameter equivalent model. So transistor will be considered with H parameter equivalent model. The input where we are applied the input is applied to the base terminal, and output is taken across the emitter terminal, and collector will be acting as a common terminal for both input and output. And we have H parameters. What are the H parameter equivalent? Already we discussed. The first element is HIC, and next we have a dependent source, voltage dependent voltage source, that is HRC, into what is the output? What is the output we are taking here? We are taking the output at the emitter terminal with respect to collector, and the current, output current is IE. What is the input current here? Input current is the base current. What is the input voltage? Input voltage is VBC, that is base voltage with respect to collector terminal, And what is the output voltage? VEC. This will be considered as H0 HRC into VEC is the dependent source, and we have another dependent source here, that is current dependent current source. This will be depending on the input current, so that is HFC into what is the input current? IB. And next we have another impedance or admittance. What is the admittance here? Is H0C is the admittance. This is the equivalent circuit for a transistor in common collector configuration. Already we discussed the general model of H parameter that is valid for all the three configuration. The second suffix here, whatever we are considering C, is representing the common collector configuration. For common emitter, already we have did this circuit, that is we considered HIE, HRE, HFE and H0E. For common collector, we will consider HIC, HRC, HFC and H0C. So this is the H parameter model of the internal logical model of the transistor. But what are the external elements which are connected here? For base terminal, between base and ground terminal, what are connected? VS and RS. So for this circuit, we will connect the internal source resistance RS along with VS. And the output side, if you see here, this is between emitter and ground. What is that? The element RL is connected between emitter and ground. That we need to connect here. RL, which is connected between emitter and ground, across which we are taking the output voltage. Now here V0 is nothing but VEC, output voltage. Emitter to collector voltage is nothing but output voltage. Let us take the input impedance here seen into the network is Zi, and what is the impedance which is seen into this network is Z0, and what is the overall impedance? Overall impedance is considered as Z0 dash. So this is the complete equivalent model for a transistor in CC configuration. So input is VSRS and output is terminated with RL. This is the internal logical circuit representation for the CC amplifier. Now we need to derive the parameters here. What are the parameters we need to derive here is current gain, voltage gain, input impedance and output admittance. So as already we derived in transistor amplifier analysis using BJT, that transistor amplifier analysis using H parameters, that we already did, and we considered the current gain expression here. Current gain is nothing but it is the ratio of output current to the input current. So output current is nothing but the current which is flowing through the load. So IL by what is the input current here? Input current is IB. So how can we define the current gain? It is a ratio of IL by IB, or we can consider IL and IE are in opposite direction. We can also consider this is minus IE by IB. So the current gain expression already we derived. So the expression is minus HF. HF means we will consider HFC and divided by 1 plus H0C into what is the load resistor RL. So this is the expression for current gain of common collector configuration. It is minus HFC by 1 plus H0C into RL. So already we did the derivation related to the current gain. You can refer the video related to this, that is we discussed in lecture 2, that is transistor analysis using H parameter model. Now this is the first equation. Now the second equation is input impedance. Input impedance is defined as the ratio of input voltage to the input current. So if you see here, what is the input voltage VBC and what is the input current IB? So we will take the ratio of VBC divided by IB. So the expression for ZI is HIC minus HFC HRC divided by 1 plus H0C into RL. This is the expression for input impedance, HIC minus HFC HRC divided by 1 plus H0C into RL. This derivation also we have done the related to the input impedance of general amplifier, and that is equally valid for each and every configuration.
So now let us see what are the basic methods or basic analysis of the electrical networks. So the basic methods in order to solve a big complex network is mesh.
Now third expression. What is the third expression? Voltage gain. Voltage gain is defined as the ratio of output voltage to the input voltage. If you see the circuit, what is the output voltage? The output voltage is taken across the emitter and collector terminal VEC, and what is the input voltage? VBC. So it is VEC by VBC. So it is ratio of output voltage to the input voltage. So AV is equal to the voltage gain expression is AI RL divided by ZI. So this is the voltage gain expression, and this is the third one. Next, fourth one, output admittance. So how can we define the output admittance? Output admittance is defined as the ratio of output current to the output voltage. So what is the output current? If you see the circuit, what is the output current? This is seen into the network is emitter current and divided by emitter collector voltage. So it is defined as the ratio of IE by VEC. So the Y0 expression is H0C minus HFC HRC divided by RS plus HI. This is the expression for output admittance of a common collector configuration. So coming to the conclusion, so we discussed about the H parameter equivalent model of a common collector amplifier. There are 4 important parameters here: current gain, voltage gain, input impedance, and output admittance. If you want to write what is the overall output impedance Z0 is a combination of what is the impedance seen into the network Z0, and this Z0 comes in parallel with RL. Z0 comes in parallel with RL is the overall output impedance of a given network. So from admittance, how we will get the impedance? So we got admittance here. From admittance expression, how we will get the impedance? Z0 is equal to 1 by Y0. This is the expression. And coming to the characteristics of common collector amplifier, the common collector amplifier will act as a current amplifier. It has high current gain, high input impedance, and the voltage gain is low. It is approximately equal to 1. Therefore, the common collector amplifier can be used as a current amplifier. It is not used as a voltage amplifier because the voltage gain is approximately unity. And if you see here in the circuitry, here if you see output voltage, if these capacitors are short circuited, so this is the base voltage VB, and this is VBE base emitter voltage, and this voltage is output voltage. Now output voltage follows the input voltage with a difference of VBE. So how can we write the KVL equation? VB minus VBE minus V0 is equal to 0. So therefore V0 is equal to VB minus VBE base emitter voltage, that is cut-in voltage of a given transistor. If it is a silicon transistor, the cut-in voltage is around 0.7 volt, and if it is a germanium transistor, it is 0.3 volts. So the output always follows input with a difference of VBE. That means it is emitter voltage follows the input voltage. So the common collector amplifier is also called as emitter follower because it follows the input. Emitter voltage follows the input, and the voltage gain is approximately unity in case of common collector amplifier. Now we discussed AC analysis of the circuit and H parameter model of the common collector amplifier, and current gain expression is minus HFC by 1 plus H0C into RL, and input impedance is HIC minus HFC HRC divided by 1 plus H0C into RL, and voltage gain expression is AI RL divided by ZI, and output admittance is H0C minus HFC HRC divided by RS plus HIC. These these parameters are useful to analyze the characteristics or behavior of the common collector amplifier. In this session, we discussed about the analysis of common collector amplifier using H parameter model. In the next session, we will discuss about the analysis of CB, common base amplifier using H parameter model. Thank you for watching the video.